Hello everybody, Dr. White here to talk about the indefinite integral. So, definition for you. We know about derivatives. What's an antiderivative? A function, capital F, is said to be an antiderivative of another function, call it little f, on some interval of real numbers from a to b, if the following happens. The derivative of capital F is equal to little f for all x values from a to b. So an antiderivative for a function little f is somebody whose derivative is little f. Okay? So for example, the derivative of sine of x is cosine of x. So sine of x is an antiderivative for cosine of x, and that's good for all real numbers x. But notice that the derivative of sine of x minus 17.3, well, the derivative of that function is also cosine of x. So sine of x minus 17.3 is also an antiderivative of cosine of x. In fact, if you got one antiderivative for a function, if you add a constant onto that antiderivative, the new function is also going to be an antiderivative for your little function, little f. And it goes the other way around too. This theorem says that. This is called the general antiderivative theorem. It's theorem 1 in this section. It says let y equal capital F of x be some antiderivative, any antiderivative you like, for some function y equals little f of x on that interval ab. Then every antiderivative of little f is of the form capital F of x plus c for some constant c. Add a constant to an antiderivative, you have another antiderivative. This theorem is saying that's the only way to do it. Any two antiderivatives for the same function little f are going to have to differ by a constant. So how would we prove this theorem? Well, suppose g of x was some other antiderivative. And that should be a little f of x there. Suppose g of x is another antiderivative of little f of x. So I'm going to go ahead and make that correction, and it'll show up when you're looking at these notes. Then define the following new function, capital H of x, just capital G minus capital F. Now I want you to notice something about capital H. If you take its derivative, then that'll have to be the derivative of the G minus the derivative of the capital F. Both of them are antiderivatives. Both capital G and capital F are antiderivatives of little f. So for both of them, the derivative is little f. So you're looking at f of x minus f of x, which is 0 for all of the x's in that interval AB. From that, I would like to argue that capital H of x must be a constant function. Now, you're probably already familiar with the idea from Calc 1. If the derivative is 0, the function is a constant. But why is that true? Why is that true? Let's get into this. Well, you may recall the mean value theorem from Calc 1. It says this. Imagine any old function, little f, that's differentiable. So it doesn't have to be the little f in this theorem here that we are currently working on. It could just be any little function at all. And imagine some interval of real numbers from a to b. It doesn't have to be the a and the b from the theorem 1 in this section. It could be just any interval at all. And imagine the graph of f of x, this curve here. And so here's the point a f of a, and here's the point b f of b. And suppose you connected those 2 points with a line. That line is called a secant line for the curve from x equals a to x equal b. Now, if you look along the curve between a and b, you can see that there's got to be some place in between where the slope of the tangent line is the slope of that secant line. There's got to be at least one number c, somewhere in between a and b, where that sameness of slope happens. So mathematically, it's saying there's got to be a c between a and b, where f prime of c is equal to that slope of that secant line, which is change in y over change in x, f of b minus f of a over b minus a. That's what the mean value theorem says. Now, let's apply this mean value theorem to our function h. Suppose that h were not constant on AB. I want to show you that can't happen. And so we'll assume that it happens, and we'll get to something absurd. Suppose h was not constant on AB. Then there would have to be two values, x1 and x2. Say x1 is less than x2, somewhere inside of the interval AB, so that h is different on those two values, so that h of x1 is not h of x2. Then think about h of x2 minus h of x1. That could not be 0 because the two h's are not the same. So it's either positive or negative. And then we've got x2 minus x1 on the bottom, and that's a positive number because x2 is bigger than x1. So this total fraction here can't be 0. It's got to be either positive or negative. We also know that there has to be some c in between the x1 and the x2 that equals this, because that's the slope of a secant line for the h curve from x1 to x2. There's got to be a c where the derivative of h at c is equal to that. That's the mean value theorem at work here. But we know that h prime is 0 all the time. We found that out right up here. So h prime of c has got to be 0. So then we have a terrible problem. H prime of z has got to be 0 for all x's between a and b. In particular, it's got to be 0 at c. But we've just found that h prime of z can't be 0 because it's got to be this. So h prime of c is 0 and it's not 0. That's absurd. It's a contradiction. So there must be something wrong with this initial assumption here that h is not constant. We got to throw that assumption out. H must be constant. The derivative, if the derivative of a function is always 0, the function stays constant. So there exists some number, capital C, so that h of x is equal to capital C for all the x's in AB. But that means that g of x minus f of x is capital C. And that means that g of x is capital F plus C. So there you are. The general antiderivative theorem is saying any two antiderivatives for a function have to differ by a constant. So there's a graphical way to think about this. Imagine antiderivatives for the function little f of x. All of them have to differ by constants. So if you pick any two of them, since they differ by a constant, the graphs of them will look like shifts of each other, vertical shifts of each other. They'll have the same shape, but one of them will be shifted up or down relative to the other. Okay. Want to introduce another piece of notation. If capital F prime is equal to little f, so if capital F is an antiderivative, then you can create a family of functions by adding on to capital F any arbitrary real number at all. And so you get an infinite family of functions. They all differ from each other by a constant. That family of functions is called the indefinite integral of little f. And it's written in a way that looks strangely like the notation for the definite integral of little f. But it's, as the textbook says, it's as different from the definite integral as apples are from bricks, I believe the textbook said. The indefinite integral of little f is a big family of functions. The definite integral of little f is from a number to a number and it's a specific number, it's assigned area underneath f. Very different things. So there are a lot of basic properties of indefinite integrals, or antiderivatives, if you'd like. Here's one, the power rule for indefinite integrals. The indefinite integral of x to the n, and I'm just going to start saying integral for short. The integral of x to the n is this family. X to the n plus 1 over n plus 1 plus any arbitrary constant. As long as n is not negative 1. If n were negative 1, n plus 1 would be 0, and you can't divide by 0 on the bottom. So why is this true? Well, it must be that the derivative of this function is x to the n. Let's check to see that it is. Take the derivative of x to the n plus 1 over n plus 1. Well, by the constant multiple rule in derivatives, there's going to be a 1 over n plus 1 as a factor multiplying the derivative of x to the n plus 1. And by the power rule for derivatives, the derivative of x to the n plus 1 is the power times the x to 1 less power. And so you get some n plus 1s that cancel, leading to, x to the n. There you go. Now you might be wondering, what if the n power is a negative 1? What's the an integral for x to the negative 1? Well, that's not too hard to remember if you remember that the derivative of log of x is 1 over x. Now, log of x actually is the function whose graph is this piece of what you see here. But if I were to do the graph of log of the opposite of x, then for negative numbers, the opposite of a negative is positive, I would get that graph over there that I'm shading in. And the two together make up the graph of the log of the absolute value of x. For any x that's not 0, the log of 0, remember, is undefined. And if you take the derivative of log of absolute value of x, when x is positive, you're going to get 1 over x. When x is negative, it turns out you'll also get 1 over x. The book does this. Check it out. And so an antiderivative for 1 over x that works for all non-zero x is log of absolute value of x. Tack on an arbitrary constant, and you've got the indefinite integral. Here are some additional properties of indefinite integrals. The integral of the sum of two functions is the sum of their integrals. The integral of a constant times a function is that same constant times the integral of the function. Both of those rules come exactly off properties of derivatives. The derivative of a sum is sum of derivatives. Derivative of constant times function is constant times derivative of the function. That leads to the antiderivative facts that give you this linearity property here. Now, a little caution here. That property says nothing about the integral of product. The antiderivative of f of x times g of x is hardly ever going to be equal to the product of the antiderivatives of f and g separately. So just throw that out of your mind right away. So, how would you do this? Antiderivative of this function here. Don't think of it like a quotient, because a quotient is a product. It's this times the 1 over x cubed. It's the product of two functions. And integral of a product is not product of integrals. Integral of a quotient is not quotient of integrals. It just won't work. You got to try to reduce your function to something you do know integrals for. So I would suggest here breaking up into the 3 separate fractions, and then using some laws of exponents, and I've got a 4. This reduces to 4 times x to the negative 1, and this reduces to 2 times x to the negative 2, and here I've got a 7x to the negative 3. It's nice to write in powers like that because I can think about using that power rule for integrals. Now, From here, I'm going to use linearity. So like integral of a sum is sum of integrals. 1, 2, 3. And integral of constant times function, like this, is constant times integral of the function. So once I use linearity to get that breakup, I can start to see whether I know how to find integrals for these very specific simple functions. Oh yeah, here the integral is log of x. Oh yeah, power rule, this is going to be 2x to the 1 higher power, so we'll go up to a -1, over that 1 higher power. Similarly, power rule helps me out here, giving me this. I tack on a plus c to get the full family of antiderivatives to make that indefinite integral. And if you like, you can simplify a little bit, as I did here. I cannot stress enough that every derivative fact gives you a fact about indefinite integrals. So like the derivative of sine is cosine. So the derivative of minus cosine, the derivative of cosine is minus sine, okay? So if I wanted something whose derivative is sine, I might start out with minus cosine. Think about this, minus cosine, take its derivative. So I'd have minus times the derivative of cosine. So I'd have minus minus sine, which is sine. The derivative of minus cosine of x is sine of x. So the antiderivative of sine x can be written as minus cosine x plus any arbitrary constant. Hey, the derivative of tangent x is secant squared x. So the antiderivative of secant squared is tangent x plus c. Similarly, because the derivative of secant x is secant tangent x, you get this antiderivative fact. And so on for antiderivative of cosine, antiderivative of cosecant squared, it's minus cotangent. Antiderivative of cosecant cotangent turns out to be minus cosecant. These trig indefinite integrals are just as important to be familiar with as the corresponding trigonometric derivatives. Derivative of e to the x is e to the x, and so the antiderivative of e to the x is e to the x plus any arbitrary constant. What about if I'm looking for the antiderivative of e to the kx, where k is some constant? I've got to find a function whose derivative is e to the kx. This one will work, 1 over k times e to the kx. Because when you take its derivative, you've got your constant multiple times the derivative of e to the kx, which is e to the kx times, says the chain rule, the derivative of kx, which is k. So there's some cancellation. You do indeed end up with e to the kx. So 2 more important things to be very familiar with. Here's another example. Antiderivative of 15 e to the 5 plus 4t dt. Okay, so my variable of integration is t instead of x. No worries, just got functions of t here. But I need to resolve things down into something I know the antiderivative for. I don't know about an e to a number plus constant times t, but I know about e to a constant times t. So I use a property of exponents to split this like this. Then I use linearity to pull out the constants. Then I use my new antiderivative fact to get this. And if I want, I can simplify things a bit. That's fine. Let's try another example. Antiderivative 5 sine x minus 3 secant squared plus 4x minus e to the 7th dx. Okay, so here's our function. So I can use linearity and I can use my facts. So antiderivative of sine is minus cosine, so 5 sine would have minus 5 cosine. Antiderivative of secant squared is tangent, so sure enough I should get a minus 3 tangent. Antiderivative of x, what should we do with that? Well, x is x to the 1. So by the power rule, antiderivative would be x to the 2 divided by 2. 4 times x to the 2 over 2 would reduce to 2x squared. Now, how about e to the 7th? Well, that's a constant. We want the antiderivative of a constant function. Well, like say it was 5. What's the antiderivative of 5? What function would have a derivative of 5? Well, 5x would. Okay. So antiderivative of any constant is constant times x. So e to the 7th times x. Don't get fooled and write just e to the 7th, because the e to the x rule does not apply here. You're not looking at a varying function of x. You are looking at a constant function of x here. Don't mind the background noise. Differential equations, really important part of math. Let's do a small introduction here. A differential equation is like an algebra equation, except your unknown, instead of being an unknown number, is an unknown function. So let's say I've got some unknown function y. It's a function of x, and the only thing, I'm only told 2 things about it. Its derivative, and I'm told its value at one point. So this part is why it's called a differential equation. A differential equation involves an unknown function and one or more of its derivatives. This other little piece of information is called an initial condition, telling you like the value of your unknown function at one place. And out of that, the game is to see if we could find the value of the function at all x, not just x equals 0. So I think, well, if the derivative of y is 5x cubed, then y is an antiderivative of 5x cubed. And so if I think about the indefinite integral of 5x cubed, which would be 5x to the 4th plus over 4 plus an arbitrary c, y, being an antiderivative, has to be one of those. For some value of c, that's got to be y. I just need to figure out what value of c that is. So where I am standing right now is that y is equal to this plus an unknown c. Now let me bring in my knowledge of the initial condition. On the one hand, 2 is y at 0. On the other hand, y at 0 is what you get by plugging 0 in for x in that shaded formula, which is this. And so I get an equation. 2 is this stuff that involves c. When I simplify, I see that 2 is c. So all along, y was this. That's what y is at each x. I've solved the differential equation. Let's do another example. Say you got a car, and at time t equals 0, when you are starting to observe the car, it's traveling at 25 meters per second. But at that moment, it also begins to accelerate at a constant rate of minus 4 meters per second, minus 4 meters per second squared. So like after 1 second, it'll be going 21 meters a second. After another second, it'll be going 17 meters a second. It's decelerating. So 2 questions. After how many seconds does the car stop? And how far will it have traveled between the time 0 when we start watching it and the time it stopped? Can we get this? Well, we're told something about acceleration, and we're wanting to know stuff about when it stops, when that would be when its velocity is 0. So we want to know some stuff about velocity. We want to know how far it's traveled, that stuff about position. And we think, wait a minute, derivative of position is velocity. Velocity is rate of change of position, it's the derivative. And derivative of velocity is acceleration. We know that from Calc 1. Here's where we know about acceleration, and we want to go back to velocity into position. So it sounds like a differential equation situation, really. Think about velocity at any time. It's got to be one of the antiderivatives of the acceleration. So take antiderivative, so take the integral of -4 dt. The acceleration, remember, is this constant, -4. So that's -4t plus any arbitrary c. So the velocity has to be -4t plus some particular c that we need to find out. And buried in the problem, we actually had an initial condition for velocity. When we started to observe the car, it was going 25 meters per second. When t is 0, the v was 25. Let's use that. 25 is v of 0, but v of 0 is what you get by plugging in 0 for t up here. We see that the c has to be 25, and so the velocity at any t seconds is -4t plus 25 meters per second. Well, when's it going to come to a stop? That's when velocity is 0. So that's when -4t plus 25 is 0. Solve that for t. At 25 over 4 seconds, it comes to a stop. How far will it have traveled by then? Well, now we're asking about position at a certain time. So can we get a general formula for its position at any time t? Well, position at time t is an antiderivative of velocity. And we don't know, like we weren't told like its initial position, but I'm just going to say that it's at 0 feet at time 0. 0 feet from its starting point, and then we'll just find out like how many feet it is from that initial starting point. So we know that s of t has to be one of the antiderivatives of -4t plus 25, the velocity. Take the antiderivative and you'll get a -2t squared plus a 25t. Add on a plus c to get the full family of antiderivatives that make up the indefinite integral. S of t has to be one of these. Find the c. Well, you're 0 feet from the start at time 0, but you're also this many feet by plugging in t equals 0. Once again, we're finding that c is 0. It doesn't always work out to be equal to the value of the initial condition, but it does in these examples. So this time, s of t is just this, plus a 0. So how far will it have traveled? Well, just plug in the time it stops. Figure it out. And I worked with it and simplified it, and I got 625 divided by 8 meters. I should point out that there's actually a graphical solution for this. Think about the velocity curve, y equals v of t. So this horizontal axis is the t-axis, t in seconds. The vertical axis is the velocity axis, meters per second, or the units. And at time 0, here's 0 on the x-axis, your speed is 25. At time 25 over 4, your speed is 0. And you're decreasing 4 meters per second every second. You're decreasing at a constant rate, so draw a line for your v of t. Now, think about the area underneath that curve from 0 to 25 over 4. Do you remember what we were kind of figuring out in previous sections? Is that the area underneath a rate function is going to be the net change in the original quantity. Velocity is a rate of change of position. Area underneath velocity should therefore give you how much the position changed. What's the area? 1/2 base times height for a triangle. 1/2 base, height. Look at that. We're still at 625 over 8 meters. Let's try a couple more. Number 33 in the homework, always, try out some odd numbered problems, look at the answers in the back of the book, see how you're doing, ask about ones in class that you had trouble on. I'm picking an odd numbered problem here. indefinite integral of secant theta times secant theta plus tangent theta. That is the product of two functions, but I don't know about the integral of a product. So I go ahead and multiply it out. And then I get some success because this will be the sum of integrals. Integral of secant squared is tangent. Integral of secant tangent is secant. Plus a c, and we're done. How about number 19? Integral of 1 over the cube root of x. Write that as a power, and you're ready to go. X to the 1 more power over the 1 more power. So that's x to the 2/3 over 2/3, or if you like, 3/2 x to the 2/3. Don't forget to tack on the plus c to get the full family that makes up the indefinite integral. Okay. How about number 65? It's another differential equation. It's what we call a second order differential equation because it involves the second derivative of the unknown function. We've got this unknown function, little f of t. And its second derivative at all t's is t to the minus 3/2. And we're told two things about the unknown function. We're told its derivative when t is 4, and we're told its value when t is 4. Can we find its value for all t? Well, I'm going to start by trying to find f prime of t, because f prime is an antiderivative of f double prime of t. So f prime of t has got to be one of the indefinite integral family. And integral of t to the minus 3/2 is t to the minus half over minus half plus a c. Let me use my initial condition. 1 is f prime of 4. Yep. But f prime of 4 is what you get by plugging in. T is 4. Plug that in. I got a 1 over square root of 4 is my 4 to the negative 1/2. Minus 1/2 goes to a 2 on the minus 2 on the top. Do some work, and I end up with a minus 1 plus c being equal to a 1. And that equation can be solved, and we find that c is 2. So f prime of t is that all along. Now let's go for f the same way. It's an antiderivative of f prime, so we look at the integral of f prime, use the power rule on f prime, and we get this stuff for our antiderivative. Plus a c makes the full family. Now we need to determine what c is consistent with this knowledge about f. 4 is f of 4. It's also what you get by plugging in 4 into the formula for f of t. Work on it a while. You find that c is 4. So there's the value of f at any t. So that's really great. Thought I would maybe try one more problem. And this one's got a picture to go with it in the book. So let me switch over to the textbook if I can find it. Yeah, here we go. So in the exercises, let me look down to maybe number 39. Yeah. So here's a figure that's got graphs of several functions. There's y equals f of x on top. And there's 3 functions here on the bottom, a, b, and c. And my question is, which of the graphs, a, b, and c, is not the graph of an antiderivative of this function right here at the top? Well, the quickest way I can think to solve this is that I notice that the a function and the c function have exactly the same shape, except that they're vertical shifts of each other. Can you see how the a function looks like the c function, except it's been like shifted up by a little amount? Now the b function has the same shape too, but it's a horizontal shift of the c function. Now remember, antiderivatives for a function have to be vertical shifts of each other. So if 2 of these things are antiderivatives and 1 is not, well, the a and c, they better be antiderivatives. The b is the one that's not. Okay. I think that's enough to get you started on this section. So I will go ahead and quit for now and see you again soon.